coming. So today, Hyunwoo will give a talk on Dirac's theorem. Right? Please.
Okay, thanks for the introduction. I didn't expect this many people. and as a member of IBS EcoPro group, my research interest lies in extremal combinatorics. I think many problems in extremal combinatorics can be classified into three types of problems. First one is Lam's type, second one is Coulomb type, and third one is Dirac type problems. And I usually Dirac type problems are stated as like if we have a sufficiently good local property, then globally there exists a very big structure. So since my talk is about a high-dimensional Dirac theorem, in this talk I will find some very big structure in the given set of hypergraphs. So I will find this structure in the collection of hypergraphs. So you can see, observe that these colors are induces triangle, and indeed these triangles are triangle decompositions of these complete graph on 9 vertices, and all these triangles have different colors. I will say this structure is transversal Steiner triple systems. So to understand this structure more in detail, let me introduce some several definitions. So the first one is combinatorial design. We say design with parameters n, q, r, lambda is a q uniform hypergraph such that every r subsets contained in exactly lambda many hyperedges. And especially if lambda is 1, then we say such designs is Steiner systems, and especially if n3 to 1 design is a Steiner triple system, and I will abbreviate it as STS. And maybe this is the most famous example for the Steiner triple.
Sorry, but the lambda subsets of size q?
Yeah, size q. Because we consider this design as a q uniform hypergraphs. So maybe the most famous example for the Steiner triple system on 7 vertices is this figure, plane. You can consider these lines as C uniform hypergraphs, and you can easily observe that every pair of vertices are contained in exactly one line. Okay, so this is the Steiner triple system. And does design with given parameter always exist? It is not. So you can easily observe that by double counting. If n, q, r lambda design exists, then q minus I choose r minus I must divide lambda times n minus I choose r minus I for i's in this range. You can easily check this by some simple double counting argument. And for the and we will say this condition, this divisibility condition is a divisibility condition, and the divisibility condition for the Steiner triple system is n divided by 6 must residue by 1 or 3. Okay. Then maybe the most natural question is this divisibility condition is the only barrier to the existence of design? So this conjecture is so-called existence conjecture. And it states that if for all sufficiently large n that's satisfying this divisibility condition, then it contains NQR lambda design. And this existence conjecture was a very long-standing conjecture, and now it becomes a theorem by Kibas in 2014, and later it was more reproved by this Kuhn, Low, and Ostus. So Kibas uses some random algebraic absorption method. So he basically using the absorbing method with random algebraic structure, and Glock et al. Using a iterative absorption method, which is a purely combinatorial way. Our main theorem, I will use this iterative absorption method. So now let's move on. So these are, so far we are discussed about the combinatorial design. Now let's move on to some Dirac type theorems. So one of the most classical theorem in graph theory is maybe Dirac's theorem, which asserts that if minimum degree is roughly at least 1/2 of the number of vertices, then G contains a Hamiltonian cycle. So if the order of G is even, then it contains a perfect matching. And this was famously extended to Heiner-Sammet's theorem, which means that if minimum degree is sufficiently large, then this G contains a perfect clique factor with size R. And in 2006, this was also extended to a hypergraph version by Loder, Luchinsky, and Sameredi. If K minus 1, let H is a K uniform hypergraph, and assume its K minus 1 codegree is at least half of the order, then H contains perfect hypergraph, perfect matching. Here the K minus 1 codegree means, so for given set of K minus 1 vertices, we say the K minus 1 codegree is the number of hyperedges that containing these vertices. Okay. Okay, so now let's move on our next keyword, high-dimensional combinatorics. So high-dimensional combinatorics is initiated by nonlinear. You can consider graphs as one-dimensional simplicial complexes, and the idea of the high-dimensional combinatorics is let's do the combinatorics on k-dimensional simplicial complexes. You can consider a perfect, in classical graph theory, you can consider a perfect matrix as a collection of one-dimensional simplices, so collection of edges such that every zero-dimensional simplex, so zero-dimensional simplex is indeed a vertex, is contained in unique one-dimensional simplex. So this is a definition of a perfect matching. Then the next natural question is, what is a two-dimensional analog for the perfect matching? And indeed, the answer is a Steiner triple system. Because Steiner triple system is for every one-dimensional simplex is uniquely contained in two-dimensional simplex. You can consider three uniform hyperedges as a triangle and pair of vertices as a one-dimensional simplex. Then the definition of a Steiner triple systems is exactly matches the two-dimensional analog perfect matches. Okay, so our result is making some Dirac type theorem for the two-dimensional combinatorics. So it will be stated like this: for a given three uniform hypergraphs H with some certain minimum codegree condition, that it contains Steiner triple systems. Okay.
Can you repeat what the definition of codegree?
In here, the codegree means the number of hyperedges, that containing these pair of vertices. Yeah, the number of vertices. Okay. And this is our some easy version of our main theorem. So if n satisfies the divisibility condition and n is sufficiently large, then for every three uniform hypergraphs H with n vertices with minimum codegree at least this number, then H contains Steiner triple systems. And indeed, we proved much more stronger theorem. To understand the main theorem, we need to define some notion of transversal. I think I don't have that so much time, so
Can you show them the statement with you only the 10 seconds?
Okay, okay. So it basically so that if minimum codegree is sufficiently large, then it contains a Steiner triple system as a sub-hypergraph.
So, yeah, go ahead.
So when H is the complete Then could you get the tight bound or?
H is a complete. What do you mean? H is a complete stream hypergraph. Then
Yes.
there always exists a Steiner trip system.
Yeah. Okay, yeah. But,
Yeah.
yeah.
Is this number tight?
Not tight, but I will make it in some sense almost tight. After our main theorem. Yeah, to state our main theorem, we need to do some fractional threshold and some other things. So, yeah, anyway,
Do you have orange type vision?
I don't know. Maybe no, because I didn't make it. So maybe no.
Do you think that we can hope for the constant lower bound for the conclusion? Constant lower bound for the conclusion.
Yeah, we have a constant low. We have a lower bound.
This is a lower bound which is
Literal.
so it depends on n, right? So
Yeah, it depends
can
on-
we hope for the constant lower bound which does not depend on n?
No. Indeed, we can construct that the minimum codegree is at least 3n/4 minus 10, but it does not contain such alternative system. We will construct such hypergraphs. Yeah. Okay. I will skip the first paragraph and I will define what is transversal Steiner trip systems. Let this curly H be the collection of 3 uniform hypergraphs on common n vertex at V. The number of hypergraphs contained in this curly H is n times n minus 1 over 6, which is exactly the same number of hyperedges in the Steiner trip systems. And we say this collection of hypergraphs H contains a transversal Steiner trip system if there exists 3 uniform hypergraph F on the vertex at V, such that the F is a Steiner trip system and such hyperedges comes from the different hypergraphs in curly H. So basically it looks like this. So it is so we take V as these 9 vertices and assume we have colored hypergraphs on these 9 vertices such that H1 to the H12, and then you can, and indeed another definition of Steiner trip system is a triangle decomposition of a complete graph. You can consider these triangles as hyperedges comes from the colored hypergraphs. So then you can observe that this is indeed a Steiner trip system, and each triangle has a different color, so it is a transversal. This structure is a transversal Steiner trip system.
Can you see the statement again? This is definition, right?
Yeah, it is a definition. Definition, and the figure is just example. So this bijective function is just the hyperedges comes from the different colors.
In the last line, you mean E is contained in H of V only?
Yeah.
Rather than is that typo or
Just yeah.
Yeah, just not V only.
Yes. Just the. Yeah, thanks.
Oh, you mean F is the union? So the edge set of F is kind of union of the H's, or?
Yes, F is a new hypergraph such that each hyperedges comes from these different hyperedges, and these hyperedges indeed forms a Steiner trip system.
It's like a colorful version.
Yeah, colorful
H1,
version.
H2 are one color. So you have a rainbow copy of Steiner trip system.
Yeah.
But each HI only has a one edge then, right? Or
Is definition. So this transversal Steiner system may not exist in some certain collection of hypergraphs, and it will be looks like this colorful Steiner trip system. Yeah. Okay. Okay, and now we will introduce some concept of a fractional Steiner system. To understand this, let me define two shadow of H. Let H is three hypergraphs, three graphs, and we will denote as H to these two as a two shadow of H, such that the vertex set is the same vertex set, and the edge set is just obtained by replacing every hyperedges of H by a triangle. So H2 is indeed a graph such that if H looks like three uniform hyperedges of H are indeed, it looks like say this, then in its two shadow is defined by like a graph by replacing each hyperedges as a triangle. So this is a two shadow of H. Then now we can define a fractional Steiner system of H. So this is a high dimensional version of a fractional matching. So it is indeed a weighted function phi on these edges of H to 0, the real number 0 to the 1, such that the number of weights that containing some certain pair is bounded by 1 for every pair E that is contained in the edge two shadow of H. And we will say this is perfect if this inequality is indeed equality for edge E in the edges of these two shadows. So it means that there is some weight function on these hyperedges such that every pair, the number of the summation of the weights that containing these two this pair is exactly just one. This one is bounded by 1, and if they are all equal to the 1, then we will say it is a perfect.
So you don't care about the pair of vertices which are not.
Yeah,
the
we don't
same
care
edge.
about. Yeah.
But in the definition of STS, you do care, right? No, maybe.
Yeah, we do care.
Oh, is it?
So indeed, in the just recall the fractional matching in the classical graph theory, the matching, it should be incident with at most one edges, but the fractional matching is allowed to incident with many other edges, but the summation of weight is less than 1. So in some sense, this is a two-dimensional fractional matching.
But in the Steiner triple system, definition says that for any set of size 2, you have same number.
Yeah, exactly 1.
Yeah.
Yeah.
And
Maybe it is related when H is complete, so here H is arbitrary.
Yeah, we
oh,
will
this. Okay.
we will just give some nice weight such that it behave like a Steiner triple system. Okay, so just
Okay.
and why we will give this fractional, we consider this fractional Steiner system because we are working on some Dirac type problem, so it maybe behaves far from the random like, but if we consider constructing some nice fractional Steiner triple system on H, then respect to this fractional Steiner triple system, the whole system somewhat behaves like a random like. So this is why we are consider the fractional Steiner triple system. And now this is definition of our crucial parameter delta epsilon. This is defined by, this is indeed a function of epsilon, which is infimum of the set of the real number delta that's satisfying this property. It means for every 3 hypergraph H with sufficiently large number of vertices, if codegree, minimum codegree of the if the minimum degree of 2 shadow H is sufficiently large, and also for every pair that is contained in these 2 shadows, its codegree is also somewhat large, then it contains a perfect fractional Steiner triple system of H. So we will define this delta type epsilon as like this, and we will denote by delta type star to be the right limit of this function as epsilon goes to 0. And indeed, if you look carefully this definition, you can observe that this delta type epsilon are monotonically decreasing as epsilon approaches to 0, and it is bounded so by the bounded monotone convergence theorem. This right limit is always exist.
So what is f? Just means fractional.
Oh yeah, just
And
means
then
fractional.
what is weight function for this fractional Steiner system?
We don't know. Just if it exists, if it contains means if there exists fractional, perfect fractional system. Yeah, perfect fractional
Some
system.
of the weight has to be included.
Yeah, just
Really
existence.
everything.
So any weight function? So sorry, could you go back to just one slide?
Okay. Yeah. The definitions are too confusing. I understand.
Okay, sorry, yeah.
Yeah. Okay.
So let me ask you a question. What is the delta in the second inequality, the right hand side with the second inequality? Yes, the delta.
Oh, this is the delta that satisfies. If this delta satisfies this, then we will collect such delta and take it the impimo. And so you can intuitively consider this delta type star is threshold for the existence of perfect fractional Steiner triple system. So this is just a fractional threshold. You can just consider.
May I have a question? So delta HE should be rather DHE in the slide, I think.
Oh yes. Yeah, this should be DH.
Degree of the
degree of the H.
Oh.
Codegree of the. Okay, so you can consider this delta type star as a threshold for the existence of a fractional Steiner triple system, perfect fractional Steiner triple system. And now this is our real main theorem. Let this H is a sufficiently large collection of 3 uniform hypergraphs, where n satisfying the divisibility condition, and every hypergraph contained in this collection, if it has this minimum codegree at least this number, then there exists a transversal Steiner triple system on V.
So do you find the fractional transversal first and then find the
Yeah, exactly. Yeah, and also we prove that this function delta type epsilon is uniformly bounded by this number, which is smaller than 0.88 for all epsilon. So it means this the fractional threshold is bounded by that number. So combining these two results and just eliminate the transversal condition, then we get our easy main theorem. And the proof of this second theorem uses Max-Flow-Vinker theorem, but I will not explain how to prove that. I will explain how to prove our main theorem, and also we will not consider about the transversal because this transversal part is too technical. Okay. And indeed, this 3/4 in this coefficient is sharp. So it means there exists and for every n, there exists n vertex 3 graph H with minimum codegree at least 3/4n minus 10, but it does not contain a Steiner triple system. So in some sense, if we can show that this fractional threshold is less than or equal to 3 over 4. If you once you prove that, then you get the asymptotically tight threshold for the Steiner-Tripp systems. Dirac type theorem for Steiner-Tripp systems. So this is why I say our main theorem is in some sense almost tight. Okay.
Do you think that the fractional threshold is actually smaller than 3 over 4? Or
Yeah, indeed. I expect the fractional threshold maybe 2 over 3, but it is very hard to prove it. Indeed, some related problem with this theorem is Nash-Williams' conjecture, which is one of the very long-standing open problem, and some several approaches to solving the Nash-Williams conjecture is considering a fractional threshold, and fractional threshold and conjectural threshold is still has some gap between. So I think for this problem, to reducing the gap between the fractional threshold and the conjectural threshold is this lower bound threshold is somewhat very hard. Okay. So yes, so this proposal says that this 3 over 4 in the coefficient of our main theorem is sharp, is the best possible.
So in the main theorem, you have this delta f star, right?
Yes.
And it's bigger than that.
So now if one can improve this next for link up part. so
Yeah,
you
maybe,
One you can
yeah.
improve the integral, right?
Yes. And indeed, I didn't optimize this second theorem, so maybe do linear programming more carefully, then it will be improved. I didn't focus on this part. So these are our main theorem. Okay. So now let's move on to the proof sketch.
Can you draw this?
Oh, sorry.
Can you draw this example?
I forgot it, but I can do it because it is a bit. So, we basically have a partition of vertices which are almost balanced, but maybe with some parity condition. Maybe we will take this as a odd, and even. And in here, if my memory is correct, we will put every triangle like this, and triangle, and then originally we had is yeah, and triangle baby. Then it satisfies the medium codegree condition, and if you check the parity carefully, if there exists a Steiner-Tripp system, then some parity issue arise. So there is no Steiner-Tripp system.
Is it known that if it's uniformly dense, then maybe it's 0?
Uniformly dense. So I didn't consider about it, but I think if uniformly dense, then the density would be close to 0. I cannot sure about it.
Actually, the top left is empty.
Yeah, indeed, this part is empty. Now let's move on to the proof sketch. So our basic idea is using the absorbing method. And since our main theorem is finding a very big structure in the hypergraphs, then how to finding a spanning structure in the given dense structure? the answer is, the one possible answer is by using an absorbing method which was developed by Loder, Luczynski, and Samarady. The absorbing method is typically consists with these two steps. The first one is finding almost the plane structure first, and then absorbing the uncovered structure by using some very good properties of the host structure. So for example, let's consider if we want to finding a Hamiltonian cycle in dense graph. You can observe that if every vertex is contained in sufficiently many triangles, then by taking these pair of vertices uniformly random and do some probabilistic method, you can indeed constructing a path sufficiently large and also not so large path such that if there is some uncovered vertices which has a boundary size, then there is also looks like these paths also exist. So in some sense you can absorbing the uncovered vertices. So if we want to finding a Hamiltonian path, Hamiltonian cycle in this graph G, we will first finding this absorbing structure in here, and then absorbing structure, and then extend this absorbing structure to almost spanning Hamiltonian cycle, and then we have some small number of vertices in here. Then by using this absorbing structure, we can extend. We can absorbing this uncovered structure to make a full Hamiltonian cycle. So this is the basic idea of absorbing method. Okay. But there is limitations of standard absorbing method for standard triple systems. To do if you want to do some global absorption for standard triple system, then it requires a very big absorbing structure, but that structure is too big and too complex, so it cannot be embedded in the given hypergraphs. Okay, because for the Hamiltonian cycle and some perfect matching should absorbing just the vertices, but for the standard triple systems you should absorbing the pair of vertices. So it requires too big absorbing structure if you want to absorbing just a one time. Okay. Then how to overcome this problem? The idea is using iterative absorption method. So iterative absorption method is if you cannot absorbing the uncovered structure just one time, then in a one time, then just iteratively absorbing the uncovered structure. So this iterative absorption method has some several steps. Typically has several steps. The first step is finding some sequence of a vertex subset which we will call the vortex, such that the size of vertices rapidly decrease, but this decrease the reduced vertex subset has sharing some very nice structural property. And in my paper we indeed prove the transversal version, so we make the transversal vortex. So it looks like this. So this is a whole structure, and we taking a small structure which shares some similar structural property, and do it this until we reach a very small set. Okay. So this structure is called the vortex, and then we will embed the so-called exclusive absorber. So exclusive absorber means that it is an absorbing structure that can absorb a constant size of uncovered structure. So this absorbing structure is also, its size is also constant. So in what I mean is, okay. So in this final vortex, there are possibly uncovered structure in the last part after we do the iterative adsorption, and we will embed some exclusive adsorber in this large set first, okay, such that if there is some pair is remain uncovered, then basically this adsorbing structure is can adsorbing this uncovered structure. Okay. So the second step is constructing this exclusive adsorber and embed it. The third one is finding the almost spanning structure in this part outside the vortex. Okay. We will find the almost spanning structure in the outside of the next vortex. Then there are possibly uncovered pair in this vortex. Then we will, in some sense, iteratively absorbing this uncovered vortex by using some small number of structures in this next vortex. So in the Steiner triple system is decomposition of triangles. We can do like this by, and these edges are chosen from uniformly random. So combined with some closing method, you can indeed absorbing these uncovered edges by using small number of structures in the next vortex. Okay. And we will do the same thing in this vortex, next vortex. Do the almost spanning structure, finding the almost spanning structure, and iteratively absorb the uncovered vertices, uncovered pairs like this, and do this again, and we finally reach this green one. Okay. And then we now absorbing these uncovered pairs in green one with this pre-embedded exclusive adsorber. Okay. Then we get a Steiner triple system. So this is a basic concept of iterative adsorption. So the first step can be done by having some Chernoff bound type inequality, and the fourth one and the fifth one is somewhat easy. So I will explain how to find the embed the exclusive adsorbers and how to find the almost spanning structure. So now, so let's consider about the exclusive adsorber first. Let G be a graph and A be a 3 graph, and we say that G and A are triangle disjoint if the triangles of this graph G and the 3 uniform edges of H are disjoint. Then we will say these two graph and 3 graphs are triangle disjoint. And we will now define a triangle adsorber for G, which is a 3 uniform hypergraph A, such that these two graph and 3 graphs are triangle disjoint, and the two shadow of A contains a G as an induced subgraph, and both A2 and A2 minus G has a triangle decomposition. So it means that let's assume we have a G in here, a graph. There exists a 3 graph A such that the two shadow A contains a G as an induced subgraph, and it is a triangle disjoint. And two shadow of this whole A also contains a triangle decomposition by using the hyperedges contained in A. And also the outside of this G also contains a triangle decomposition which are using the hyperedges of A. So this definition is, in some sense, this structure, this hypergraph A can absorbing this graph G. Okay. So since we are working on a Dirac type problem, so our host structure is made out of complete graph. So if we construct an exclusive absorber correctly, then it should be embedded to our given hypergraphs, right? So to do that, we will embed it greedily. So to achieve this, I will define edge degeneracy, which is extended concept of a usual vertex degeneracy. So let H be a 3 graph and F be a graph as a induced subgraph of 2 shadow over H. We will define H rooted edge degeneracy of H as a minimum smallest integer D, such that there exists a vertex ordering outside of the vertex of F, such that it means if we have a F like this, and we have a vertices such that V1 to the V H and minus V F, such that the number of pairs in F such that together with V forms a hyperedge is bounded by D, and for this V2, the number of pairs inside these together with V1 that making a 3 uniform edge with a V2 is also bounded by D. And again, in this V3, the number of pairs inside these vertices that making a hyperedge with V3 in H is bounded by D, and so on. Okay. So this is an extension of vertex degeneracy to edge version. Okay. And we constructed that if G is a triangle divisible graph, which is it can be possibly absorbed. So just consider that G is just a graph, then we can construct an exclusive absorber A for triangle absorber A for G, such that whose G rooted edge degeneracy is almost 4. Why this is useful? Because we have that delta minimum codegree is at least 3 over 4 times n. So this edge degeneracy is almost 4 means we can greedily embed this exclusive absorber in this edge, because if there is a G with a constant size, and let this V1 to the this V is ordering that defined like this, then by this one it means that if you want to do this V1 into a H, it means there are at most 4 parallel vertices in G, such that together with these pairs and V1 forms a hyperedge. And there are at most 4, and this with minimum codegree condition, and do some Pigeon principle, there are at least 1 vertex here that can embed like this. Okay. And now let's move to V2 and do the same thing again. then we can embed this exclusive observer in H. Okay.
So would this lemma be false if 4 is 3? If you change the 4 into 3, would this lemma be false?
Sorry, this lemma.
Like if the 4 is changed into 3, would that be false?
Yeah. We cannot change this. We cannot replace this 4 to 3. If we can replace this to 3, then maybe the threshold would be 2 over 3. But I constructed the hypergraph with minimum codegree is 3 over 4 times n, but it does not contain so standard system. Okay. Yes. So by this lemma, we can embed this exclusive observer in our hypergraphs. Okay, so this is how we construct indeed I didn't construct it yet, but I will not explain it. But anyway, we can embed it. So now let's prove how to finding an almost span structure. So let H is a graph, 3 graphs, and we will define an auxiliary hypergraph of H such that its vertex is indeed a pair of vertices of the original hypergraph, and the edges are defined like that way. So it means, so in some sense, you can consider this auxiliary hypergraph is some line hypergraph. So it means that we have a hypergraph H like this. This is a hypergraph H, and we will construct an auxiliary hypergraph as a pair of its vertices. So this is become a vertex, 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 and so on. And we will adding a hyperedge if these 3 edges are indeed forms a triangle, in the forms of hyperedge in the original hypergraph. So it means that we note that these 3 vertices are representing this edge, and this edge, and indeed these are forming a hyperedge in H. So we, in the auxiliary hypergraph, we put hyperedge, hyperedge, and hyperedge.
But in the slide you have vertex for every pair of vertices.
Yeah.
But in the picture you have a vertex
I
for
didn't. Okay. So yeah. Okay. Yes. Okay. And one crucial observation is if H contains a Steiner system, it is equivalent to this auxiliary hypergraph contains a perfect matching. Okay, you can easily check that. And also this auxiliary hypergraph is linear, indeed a linear hypergraph by its definition. So now we will define a new notion of a pseudo-randomness. Since it is easy to finding a almost perfect matching in a pseudo-random hypergraph, so I will introduce a new definition. Let d delta tau be a positive real number, and let H be a multi-hypergraph. We say that this is a d tau delta pseudo-random. If H is almost regular, it means the vertices of the H, each degree is contained in the range of d plus minus tau d, and its maximum codegree is bounded by delta times d. Then we will say this is a d tau delta pseudo-random. And why this notion is useful? Because a very famous result of Pippenzer and Spencer says that if tau and delta is sufficiently small, then this d tau delta pseudo-random hypergraph contains an almost perfect matching. Okay.
Sorry, but so Why is it called a pseudo-random? Because in the condition there is no randomness in
Yeah, but no randomness, but
Yeah.
you can consider it in some sense A-dash linear hypergraphs
Ah,
almost over every vertices are in some sense regular, close to regular with high probability, and also its codegree is relatively small. So these hypergraphs share some random property, shares the property with the random graphs. Yeah. And indeed, we did. If we want to finding a transversal version, we did a very strong pseudo-random list. So we will define to do that. We will define fractional matching and pseudo-random list for the fractional matching. So the fractional matching is just a usual fractional matching. It means it is a weighted function on the edges of H such that every vertex V, the summation of the weighted edges that incident with V is bounded by almost 1 for all V, and if these equalities are equalities for all V, then we say this is a perfect fractional matching. Okay. And we will denote by d psi V as a weighted degree of V, the summation of the weights that incident with V. And similarly, we define large delta to psi H as the maximum weighted codegree of H. And now we define d tau delta pseudo-random fractional matching for a fractional matching psi. If every V in VH, we have that this weighted degree is regular, almost regular, which is 1 plus minus tau times d, and its weighted maximum codegree is bounded by delta d. And why this is useful if we want, since this fractional matching is in some sense a linear relaxation, so it gives much some flexible structure than the just a discrete object. And if we if we increase the multiplicity of the hyper edges based on this fractional matching, so do some discretization, we can convert this pseudo-random fractional matching to the very pseudo-random hypergraphs. So by this fractional matching, we can produce a highly pseudo-random hypergraph. And this is our main lemma, which makes how to produce highly pseudo-random fractional matching. I think this lemma is most important, crucial lemma in my result. Let C and D be the natural number, and let gamma delta tau is a real number, and let these inequalities hold. And let H be a multi-hypergraph such that its minimum degree is at most D, and its maximum codegree is bounded by delta times D. So since it is only the lower bounded, it could be a bit far from the random like. And now assume that for every sub-hypergraph F in H with bounded maximum degree, and assume if we remove this F from H, then it still contains a perfect fractional matching. So this is the assumption. Then H contains 1, 0 eta pseudo-random fractional matching psi. So if we using this lemma with some proper parameters, we can get a very pseudo-random fractional hypergraph, fractional matching. Okay. So by using this lemma, we can prove that if H is a 3 graph with minimum codegree and this fractional threshold plus some little 1 times n, then we can prove that and also do some discretization. We can prove that there exists multi-hypergraph F on the auxiliary hypergraphs of H, such that the simplification. So it means we replace multiple edges to a single edge. So the simplification of h, f is indeed the sub-hypergraph of this auxiliary hypergraph. And this f is n to the 4, 1 over n, and log square n over n pseudo-random hypergraph. Okay. Since f is highly pseudo-random, and its simplification is a sub-hypergraph of h ox, if we finding almost perfect matching in this f, then this almost perfect matching is contained in this auxiliary hypergraph by the first property. And by the second property, the f is a pseudo-random. This f contains almost perfect matching, and we observe that the almost perfect matching in auxiliary hypergraphs is indeed produce almost full Steiner triple system in the original hypergraphs. So by this lemma, we can prove that our hypergraph contains almost full Steiner triple systems. And also, this almost Steiner triple system is, in some sense, highly pseudo-random. So we can do the iterative absorption without any problem. So by this, we can prove there exists a Steiner triple system. Now, these are some concluding remarks. Of course, this is very easy conjecture. Statement is very easy because we can indeed replace this conjecture means we can indeed replace the minimum codegree condition to 3 over 4 times n plus some constant c. Okay, and I think if this conjecture is true, then it would be very nice result. And another conjecture is about the resolvable Steiner triple systems. So the resolvable Steiner triple systems is also a Steiner triple system, and it can be, and additionally, it can be perfectly decomposed into perfect matchings. Yeah, we say this is a resolvable Steiner triple system, and the divisibility condition for this resolvable Steiner triple system is, and the residue of n by 6 is 3. So this conjecture means if for sufficiently large n with divisibility condition and also the minimum codegree condition lists roughly 3 over 4n, then it also contains a transversal resolvable Steiner triple system. And so this is our last conjecture. And thanks for listening.
All right, any questions? Okay.
In the last conjecture, do you have any bound on the minimum codegree for the H transfer resolvable? So do you have any so did you obtain any minimum codegree condition?
For the resolvable, no, I didn't consider.
Other questions? Was there some previous result on this direction where a linear bound implies the existence of a STS?
No, there is no previous result about this. So I also wondered about it. I think this is very natural problem, but nobody considered about this direction.
So in this problem for Steiner triple system, how can I say this? So the subset which is contained, it has the size difference 1 from the size of the things that contains, right?
Yeah.
So, but if the difference becomes large and large, then can you also have the similar kind of linear bound or to conclude a similar?
Maybe I expect it will be linear lower bound.
Linear lower bound.
But I cannot sure.
So this is this kind of result is the first observed by you.
maybe.
I see.
How about the other types of design?
I initially considered it first, but design these two complex objects, so it's hard to handle. So this is why I just only do the standard system.
What is the next easiest design?
I don't know. Indeed, perfect matching is also considered as a design, but it is already considered this type of a problem. The perfect matching are already extensively studied, and this is the first move towards to the second, higher design. But I don't know what will be. The designs are too difficult.
Any other questions? If not, let's thank the speaker.